Hello, ladies and gentlemen. Today we're going to be covering 7.8, which is arc length and surfaces of revolution. So in past math classes, we had found the length of line segments. We used this idea of distance formula to find the length of a line segment. And we took the square root of x1 or x2 minus x1 squared plus y2 minus y1 squared. And then we simplified, that's how we were given 2 points and we found that line segment. So arc length is now that we don't have necessarily a line segment, we now have a curve of a segment. So it's very similar. We're going to use that formula of distance formula. So the change in x and the change in y. And we are going to be able to derive this by using kind of the idea of derivatives here. So being able to simplify this out, we're able to come up with the arc length formula. Okay, so the arc length formula is basically our integral from a to b of the square root of 1 plus f prime of x, and that's all squared. Okay, so it's always a good idea to put this guy in parentheses. So I'm going to put this guy in parentheses. This guy needs to be in parentheses. Oops, I can put it here. Let's just do it here. So this needs to be parentheses. So I'm going to put this in parentheses just to make sure you know that this is being all squared. Okay. So let's do an example. We have here a quadratic equation x squared, and the interval is going from -1 to 1, and we want to find the length of that arc that goes from -1 to 1. So what we're going to do is we're going to first find the derivative of that function. So the derivative of x squared, which is a simple power rule, is 2x. And we're going to plug that into our arc length formula. So you want to make sure you memorize this formula here. And so we plug it in, and then we can simplify. So for this problem, it looks like we're going to use a calculator here. And most of these types of problems, you're going to use a calculator because unless we could use substitution, then we would. But some of these problems, we're going to have to use that calculator. Okay. And so you'll notice that each of these problems, we are finding the derivative of the function, plugging it into our arc length formula, which is up here. Okay. The next concept is surface of revolution. So surface of revolution, we're finding the area of that. And this is when we combine the concepts of volume by rotating an arc length to find the surface area of a solid of revolution. So it's combining what we just learned about finding arc length, but then multiplying it by the function to be able to find its surface area. Okay, so whenever we do these problems are very similar to when we were finding volume, and we have to make sure it's in the right terms. So if we're rotating around the horizontal axis, kind of like the x-axis or y equals 1 or y equals -2, it needs to be in terms of x, okay? And then if we are revolving around a vertical axis like the y-axis or x equals -1 or x equals 2, then we have to make sure everything's in terms of y, okay? So our function has to be perpendicular to the axis that we're rotating around, okay? So for instance, if you have r of x, that's your y, that's perpendicular to the axis that you're rotating around. Just like this guy, when we have vertical axis of rotation, it's in terms of y. So it's this guy, but it's being rotated around the y-axis. So again, we're just doing a couple of examples. We need to make sure we know how to find the derivative of this function here. And then once we have that, we can plug it into our surface area formula. And we're using the horizontal axis of rotation because it says it's rotating about the x-axis. Okay, and so when we simplify this, we're going to end up using our calculator here. We get 3.563. Okay, notice that this example here, we're doing the same thing. We're taking the derivative of that x squared, where it's going from 0 to square root of 2. And then from there, we can put it in terms of in terms of y, because this is being rotated around the y-axis. So you'll notice that this arrow is telling us that we're rotating it around the y-axis. So this needs to be in terms of y. Okay. The last example I'm going to show you here in this lesson is called Gabriel's horn. This is kind of a paradox concept here, in that what it's saying is Gabriel's horn is the name given to a three-dimensional figure created when the functions of f of x, where we have 1 over x, on the interval from 1 to infinity is revolved around the x-axis. So Gabriel's horn is a paradox because it has infinite volume, yet an infinite surface area. All right, so it has a finite volume, but an infinite surface area, which is pretty crazy. So when we solve this and we find the volume, we find the volume by taking obviously 1/2 x, and that being squared, the integral of that, and then times pi. And so we found the volume is pi. So that's the volume. But if we apply that same concept to find the surface area, and we do the arc length, we do the surface area formula up here using the arc length, we're able to derive this where this guy here is basically the same thing as the integral of 1 over x dx, which if we take the if we antiderive this, we get ln of x, and then this is bounded from 1 to infinity, and when we solve this, we end up getting the natural log of infinity minus the natural log of 1, which the natural log of 1 is just 0. So we end up getting infinity. So what we're showing here is that this guy, this arc length here, is actually going to be greater than or equal to 1 over x. So the surface area is going to be infinity. So it's just it's a crazy concept here, because all we know here is we know that if we derive this 1 over x, we get infinity. So even if we try to take the antiderivative of this section here, it's still going to either be a constant or it's going to be infinity. So if we were to just integrate this piece, we're just able to show that it's going to infinity. Okay, so crazy concept here. We're going to go into this a lot more in detail in Unit 8 when we talk about improper integrals, which are integrals that either are discontinuous at certain values on an interval, or it either goes to positive or negative infinity. So stay tuned for that in our next unit in BC. Please, ladies and gentlemen, jot down any questions that you have. Make sure you complete your homework over this section because this is a new concept. And I look forward to answering your questions and continue on with this course. Have a wonderful day, and I'll see you soon. Adios. Bye.